Good day, we are Group 13 and we'll be solving the problem of the day. To effectively understand and solve the problem independently, it's essential to review the concept of block diagram reduction rules, which provide systematic techniques for simplifying control system block diagrams into a single transfer function. So, we will move on to our first rule, which is reduction rule 1, representation of a closed loop system. A closed loop system is one in which the output is fed back to the input for comparison. It has R as its reference input, C as its output, G as its forward path transfer function, and H as its feedback transfer function. The overall transfer function obtained from this diagram when reduced is C divided by R is equal to G divided by 1 plus G times H. Closed loop systems are primarily used to improve accuracy, stability, and overall control performance. Examples include temperature control systems, speed control systems, and automatic voltage regulators. Now, on to the second rule, which is block diagrams in series or cascaded connections. When blocks are connected sequentially, their transfer functions are multiplied. If two blocks G1 and G2 are in series, the overall transfer function becomes C divided by R is equal to G1 times G2. Thus, the equivalent transfer function is the product of the individual transfer functions. So here is a proof that shows how the transfer function is obtained from the individual transfer functions. Now, rule 3, which is block diagrams in parallel. Block diagrams share the same input and their outputs are summed. Their transfer functions are added. For two parallel blocks, G1 and G2, the overall transfer function is C divided by R is equal to G1 plus G2. Hence, the equivalent transfer function is the sum of the individual transfer functions. So here is a proof that shows how the equivalent transfer function is the sum of the individual transfer functions. I will hand over to my colleague to continue.
Okay, hello everyone. My name is Kelvin Senna, and I'll be continuing from where my colleague left off. So we have rule 7, which is the shifting of a pickoff point after the adder. Over here is our pickoff point, and our output from the pickoff point is R1. We're trying to shift it after the adder while still maintaining the same output R1. The problem with doing that without changing anything in the system is that we get R1 plus R2 as our output, which is wrong. So we are trying, what do? We have to include another adder with a negative input connected to R2. That way, our equation here will be R1 plus R2 plus minus R2, which is R1, the same as what we are trying to get. The next rule is the rearrangement of the adders. So we have R2 and R1 being further added to R3 over here and giving us this result. After passing two blocks J, we have R1 plus R2 plus R3 times J as our final output. After switching them, we still have the same output. After switching R2's other with R2's other, we still get the same output. This proves that we can rearrange any two side-by-side adders without any change in the block diagram implementation. I have rule 9, which is the shifting of an adder before a block. We have the adder here, and we're trying to shift it with the block, before the block. If we do that without changing anything in the system, our output will be changed. So what do? We have to include another block, which is the inverse of the block here. So 1 over j is being added to R1. That way we have R1 plus R2 over j. After passing through block j, we multiply it, then we get j R1 plus R2, which is the same as the output that we got before. The next one is the shifting of another after a block. Now this is quite similar to the one we did, but the difference in this one is that we include the same block connected to R2 to get the same output. Okay. So now our problem of the day over here. I want you to observe the question and see which rules can be applied to this block diagram to make it simpler and enable us to find the transfer function. Okay. So we have RS as our input going into an adder with a negative feedback loop from here with another H3 block, going into G1, another adder with a negative feedback loop of H2 with H2 block, going into G2, another adder with a positive feedback loop from with a block H1, going through G3 and J4, and then giving us our output P of S. Thank you.
We are simplifying a complex block diagram, and the goal is to combine blocks and move summing points to make the system easier to analyze. This process helps us to find the overall transfer function. So what happens in the first slide is that the third summing junction is originally after G2. We move it before G2 to simplify the feedback path. Moving summing points helps combine blocks easily, but when moving a summing point across a block, we must adjust the feedback path. The feedback signal that passed through H1 must now pass through the inverse of G2. This compensates for moving the junction across block G2. The system now shows the feedback path, H1 moving into the inverse of G2, and we realize that the fourth path remains unchanged. This keeps the system mathematically equivalent. In step 2, we adjust the feedback path. Since the summing points moved before G2, we multiply the feedback path by the inverse of G2, so the feedback path now becomes H1 over G2. We hereby also combine series blocks because blocks in series multiply, and since G2 and G3 are in series, they become G2, G3. After step 2, the diagram is simpler, there are fewer blocks, and it's easier to continue the reduction. After step 2, we realize that H2 is still the upper feedback loop, H3 remains the outer feedback loop, and the system behavior is unchanged. Thank you.
Good day, everyone. So for step 3, we focus on shifting the pickoff point in the block diagram to further simplify the system. So from block diagram reduction rules, to be specific, the rule 5 will be shifting this pickoff point from here to here, that's before the G4 block to after the G4 block, in order to make our simplification much easier and faster as possible. Okay, so to maintain the signal equivalence, we apply two key adjustments. First, since the pickoff point is moved before the G4 block to after the G4 block, we divide the feedback path by the G4, and as I'm showing you, the feedback path is from here up to here. So the block located on the feedback path is H2, so we'll be dividing the H2 by this G4. Secondly, because block G4 is now in series, so after dividing the H2 by G4, this G4 now becomes in series with the G2, G3 block. Okay, so now we'll be multiplying the G2, G3 by the G4, since the forward path gain will be changing along this particular path, and thereby making it G2, G3, G4. Alright, so in doing so, the feedback path remains equivalent. The raw system becomes much simpler. Thank you.
Good day, everyone. I'm Francis, and I'll be talking about step 4, that is simplifying the loop. So in step 4, we simplify the inner feedback loop that contains G2, J3, J4, and H1. So at this stage of the block diagram, we can clearly see a closed loop formed by forward path, which is J2, J3, J4, and feedback path, which is H1. Now, whenever we have a single closed loop, we apply the standard feedback formula, which is G over 1 plus or minus GH, where our G is the forward path gain and our H is the feedback gain. So in our case, forward gain, which is G, will be Gen2, Gen3, Gen4, and feedback gain, which is H, will be H1. And since the loop is negative feedback, we use G/1 minus GH. So the equivalent transfer function of that loop becomes Gen2, Gen3, Gen4 all over 1 minus Gen3, Gen4, H1. You notice that Gen2 is not inside the feedback path, so only Gen3, Gen4, H1 appears in the denominator. So after replacing the entire loop with this single equivalence block, the diagram becomes much simpler. Now, instead of 3 cascaded blocks with a feedback loop, we have one single block, which is Gen2, Gen3, Gen4 all over 1 minus Gen3, Gen4, H1. And the remaining outer blocks are Gen1, H2 over Gen4 and H3 stay unchanged.
So in this step, we focus on simplifying the feedback loop that includes H2 and G4. First, notice that the blocks G2, G3, G4 already form a subsystem with an internal feedback loop through H1. That inner loop has already been simplified and represented as a single block, so we don't need to worry about its internal details anymore. Now, the output of this block is fed back again through H2 over G4 to the summing junction. This creates a second feedback loop acting on the same forward path. Instead of analyzing these two feedback loops separately, we apply standard block diagram reduction rules to combine them into one equivalent block. So that's what we do here. All this divided by all this. When we do this, the forward gain remains G2, G3, G4, but the denominator now includes the effect of both feedback paths, that is H1 and H2. As a result, the entire loop is replaced by a single block that captures all the feedback behavior. So that's all what this is about.
Everyone, my name is Francis Kaboma, and I'm going to continue from where my groupmate ended. So from what he said, this and this are in parallel. That's how come they're dividing over here. And we are getting this equation. To simplify this, we just change the division sign to multiplication and exchange the denominator and the numerator, sorry. So this and this will cancel out in the end. That's why I'm getting G2, G3, G4, 1 minus G3, G4, H1 plus G2, G3, G4, H2. Yeah, that's how I'm getting this whole equation. Yeah. So we come and put this whole equation. We can't put this whole equation inside the block diagram because if we use this whole thing over here, and we are getting this equation right now. So we can't put it inside the block diagram. And we know that G1 is multiplying this whole equation over here. Let's say this is X right now. So X is representing this equation. So G1 multiplied by X in this situation. So we'll go down and we'll see G1. So we multiply G1 by the whole equation and we get G1 G1, G2, G3, G4, 1 minus G2, G1, H1 plus G2, G3, G4, H2. That's how come I'm getting this whole equation because this and this will multiply to get this whole equation. Yeah.
Hello, I'm Apia Gabriel Kofi, and I'll be continuing from where my group mate ended. From the point she ended, we obtained the expression G1, G2, G3, G4 over the expression 1 minus G3, H3, G4, H1 plus the expression G2, G3, G4, H2. And then it was obtained by multiplying these two expressions because they are in series. Now we are going to be dealing with the last part of the solution, where we are going to obtain the final feedback from this loop. And the feedback that will be obtained goes from this expression to H3 and back to this expression. And in that case, to simplify the loop from H3 to the expression obtained, it's going to be the expression obtained divided by 1 plus the same expression. And to simplify this aspect, you have to find the LCM, where the denominator becomes the LCM, and the denominator is then multiplied by this one before it's added to the numerator over here. And that is what has been simplified in this expression over the same denominator. So in that case, this is going to be divided by this. But then to do away with the division sign, we change it to a multiplication sign and we reciprocate the right side of the expression or the equation. The expression. And that is going to be changing the numerator and the denominator. That's the positions of the numerator and the denominator. And in that case, since the denominators are the same over here, when it's being reciprocated and this is multiplying, they are going to cancel out. And now we are going to obtain the numerator over here divided by the numerator over here. And that becomes our final feedback. And then our final feedback is given by the expression CS over RS, which is this expression divided by this expression. So this becomes our final solution for the problem we are to solve. So the final feedback obtained has to go through from this side to this and back to this. In that case, we use this expression to obtain the final feedback. So when we simplified this aspect, we obtained this. This divided by this has to go through some processes where this is going to be reciprocated. Then the division sign changes to a multiplication sign. And when we simplify that, we're going to obtain this, which is our final feedback, plus CS divided by RS. Thank you very much.